Good morning, everyone. I am Mr. Ish. Thank you for joining me. A very interesting and useful concept here, heat. We have to calculate the heat needed to raise the temperature of 18 grams of water from minus 50 degrees Celsius to 145 degrees Celsius. You know, when you're looking at water at minus 50, it'll be pure ice, solid ice. At 145, it'll be just entirely all steam. In between, you'll have changes in the transition, the states of water. The heat capacity for ice is 2.09. We're not looking at the units. The heat capacity for that ice is 2.09. For water in the liquid state, it's 4.184. And lastly, for water in terms of steam, it's 1.84. How do you go about with this type of question? You know you're putting in heat to raise the temperature. You're looking at something which is entirely endothermic reaction. If you're looking at water and it's going from solid to liquid to gas state, you're putting in heat and it's an endothermic reaction. If, however, you take water which is in the form of steam or vapor and you condense it and you convert it into liquid, you've generated heat. It's an exothermic reaction. Heat is released when water condenses. When you take that liquid and you freeze it, again you'll generate heat. It's an exothermic reaction because when water freezes, heat is given off. You have to keep these in mind, but we're looking at a question which involves this specific set of steps where everything is absorbing heat, so you will have energy being used up by the system to create these changes in the states. Everything we're going to talk about in this question can be represented by means of a heating curve. A heating curve of water. You have heat here, you have temperature here, degrees Celsius. We're starting here for something which is at minus 50. You can bring right here, minus 50. You're going to start putting in heat and the temperature of the water will go up. And then at 0 degrees, you'll have what is called melting of water. The solid will start converting to liquid. But during that melting phase, the temperature won't go up. Even though heat is being used by the system, temperature won't go up. It'll be a flat line over here. And then you'll start increasing the temperature up to 100. At 100 degrees, you'll have what will be the evaporation of water. But at 100 degrees, you're still going to generate another flat line as all the liquid starts converting into gas. Then you're going to start changing the temperature again up to this point, 145 degrees. At this point right here, you have only solid. At this point, you have solid and liquid. At this phase, you have liquid only. Here you have liquid and gas, and here you have just gas. At each of those phases, 1, 2, 3, 4, 5, heat is being used, and we have to incorporate all of that to calculate the entire heat needed to make that change from minus 50 to 145 for 18 grams of water, which you know is 1 mole of water. Molar mass of water is 18. Mass divided by molar mass gives you mole. Here we have 1 mole of water. There are two things you need to be familiar with before we start this, and let me just post them out for you. At this phase right here, and at this phase right here, here you'll have delta H fusion. Fusion means the conversion of solid to liquid or liquid to solid. You can either do a forward or a reverse, either the melting or the freezing of water. When you're talking about the melting of water, you're putting in heat, it's positive value. You'll have a positive value 6.02 kilojoules. If you are freezing the water, it'll be negative because then you know it's exothermic reaction, heat is released. But when you're melting water, you're putting in heat to melt it, you have a positive value. The other item you need to know here, delta H, but vaporization. Here you're converting the liquid to gas. You can have a positive value because it's endothermic reaction. Here it's going to be 40.7 kilojoules. If you're going in the reverse direction where you're condensing steam into liquid, then it'll be minus 40.7. But each of those 5 phases, you'll have heat calculations and we have to do that. Let's look at this phase 1 where we have purely solid phase. You know the equation is H is equal to mc delta T, the heat capacity calculation. You have mass times your specific heat times the change in temperature. In this phase right here, we have a mass always of 18 grams multiplied by the specific heat of ice, 2.09, multiplied by change in temperature from 50 to 0. We have a change in temperature of 50. Bring it all here into the calculation and let's do it. You'll have 18 times 2.09 times 50. I have 1881 joules, but we'll convert everything into kilojoules. Divide that by 1000. You'll have 1.881 kilojoules. That's this part. Now let's talk about this, where you have the solid being converted into liquid. Here you're looking at only this. You don't have to do a calculation because this is the amount of energy absorbed for this conversion for 1 mole of water. 1 mole is 18 grams, so we have exactly what we need, 6.02 kilojoules for that transition. Now we have to calculate this right here. The heat required for 18 grams, having a specific heat of 4.184 and a change in temperature from 0 to 100 is 100. Now notice these heat capacities. For water it's always the highest, because water, in terms of the liquid, you have a lot of water molecules close enough that hydrogen bonding is preventing the change in temperature. In ice you have a slightly lower, you have water molecules close enough that you do have good amount of hydrogen bonding, but in steam it's the lowest heat capacity because water molecules in the vapor form are too far apart. You have minimal to no hydrogen bonding, so a less amount of heat can do a great amount of temperature change. Anyhow, let's get back to this. You have mc delta T. You have 18 times 4.184 times 100. We have 75312, which I'll divide by 1000 to keep everything in kilojoules. 7.5312. 7.5312 kilojoules. Now let's look at this phase from liquid to gas. We don't need to do any calculation because for 1 mole of water, there's 40.7 and I have 1 mole. We can just make that 40.7 kilojoules. Notice how the heat of vaporization takes the most amount of heat energy to do that. Too much heat energy is required here to do this change. But remember here, nothing is drawn to scale, otherwise this line here would be pretty long to represent the amount of heat required. And the last one is a gas. To change it, to account for this transition here, you have mc delta T. You have 18 grams. In all instances, you have the heat capacity 1.84 and you have a temperature change here of 45 degrees from 100 to 45. Let's calculate this. You'll have 18 times 1.84 times 45. You have 1490 joules. Divide that by 1000 and I'll have 1.49 kilojoules. Everything here is positive because these are all endothermic reactions. All you have to do is add up this number, that, and that, and we'll have our total heat needed for this entire change from minus 50 degrees Celsius to 145 degrees Celsius for water. We'll do 1.881 plus 6.02 plus 7.5312 plus 40.7 plus 1.49. I have 57.6 kilojoules, and that'll be our answer, 57.6 kilojoules. Everything here is positive. It will take 57.6 kilojoules or 57,600 joules of heat energy to convert 18 grams of water from minus 50 degrees to 145 degrees. If supposedly the question was, what's the amount of heat released? Because you know it's an exothermic reaction for the reverse reaction where you're going from steam to ice. From 145 to minus 50. Here everything will be the same except your graph would be flipped. You see how we're going upwards? You'll start from here, you'll start going down in that direction. This value will be the same except in that case you'll have an answer minus 57.6. Positive 57.6 indicates endothermic reaction for the heating of water. Minus 57.6 kilojoules will represent the cooling of water. Exact same parameters but cooling it down from 145 to minus 50. All of these values here would be negative. You'd have a negative outcome because it would be exothermic. Remember here we have the heating curve of water, which contrasts with the cooling curve of water. But that's all for this video. Thank you for watching.